Hey there, and welcome. Today, we are pulling back the curtain on the invisible world of chemistry that is happening all around us all the time. Seriously, we're going to talk about the amazing reactions that build and completely transform our reality, from the fizz in your soda to the very air you breathe. So let's dive right in.
Really think about it for a second. We see these things constantly. You crack open a can of soda and whoosh, it's a burst of bubbles. You slice up an apple, get distracted, and when you come back, it's turned that kind of gross brown color. Or you see an old bike left out in the rain, one shiny, now just covered in flaky red rust. This isn't magic, it's chemistry. And all these things have the same fascinating answer.
And that's it. That's the big secret. One single concept, a chemical change, explains all of those everyday mysteries. It's when a substance doesn't just change its shape or form, it fundamentally transforms into a completely new substance with brand new properties.
Okay, so let's break this down because it's super important. On one hand, you have a physical change. Think about melting an ice cube. It turns into water, right? But it's still H2O. It just changed its outfit. You can freeze it again, no problem, it's temporary. But a chemical change, that's a whole other story. When you burn a piece of wood, you get ash and smoke. You can't turn that ash back into wood. It's gone. A totally new substance has been made, and that change is permanent. You can't unscramble that egg.
So if we're going to talk about these massive transformations, we need to, speak the language. And luckily, scientists have a really simple and honestly elegant way to write down exactly what's happening during one of these chemical changes.
Just think of it like a recipe. It's that easy. On the left side, you've got your ingredients. Scientists just call them the reactants. Then you've got the arrow in the middle, which basically just means turns into or makes. And on the right side, you've got your final dish, the new stuff you made, called the products. Reactants on the left, products on the right. Simple, right? It's the blueprint for any chemical change.
And let's bring it back to our soda. Here's the recipe for that fizz. You take some citric acid and you add some sodium bicarbonate, which is really just a fancy name for baking soda. The arrow shows us they react, and what do they make? They make carbon dioxide gas. That's the fizz. And a new thing called sodium citrate. See? We just described that bubbly magic with a simple little equation.
Okay, so we know what happens, and we know how to write it down. But the bigger question, the really deep question, is why? What is driving these atoms to break up with their old partners and form completely new arrangements? What's in it for them?
Well, it all comes down to a surprisingly simple goal: stability. You can think of it like this. Most atoms, they just feel incomplete. They feel unstable unless they have a full outer layer or shell of 8 electrons. It's called the octet rule. They all want to be like the cool kids on the periodic table, the noble gases, because those guys are perfectly stable and happy. Their outer shells are already full, so they don't need to react with anyone.
So to get that full outer shell and reach that stable, happy state, atoms have to connect with other atoms. And these connections, these are the chemical bonds. They're the invisible forces that hold molecules and literally our entire world together.
Now, let's look at the first main strategy that atoms use to get stable. I like to call this one the giver and the taker, and it's all about a type of bond known as the ionic bond.
With an ionic bond, this is not a friendly collaboration. It is a transaction. One atom literally gives away its extra electron to another atom that needs one. The key word here, you absolutely have to remember this, is transfer. One atom loses, another one gains.
The absolute best example is making table salt. So you've got sodium, right? It has this one lonely electron in its outer shell that it's just dying to get rid of. Ditching it would leave it with a perfect full shell underneath. Then you have chlorine, which has 7 outer electrons. It is desperate for just one more to be complete. So sodium, the giver, transfers its electron to chlorine, the taker. Now sodium is positively charged, chlorine is negatively charged. And what do opposites do? They attract. And boom, they lock together in a super strong ionic bond.
But what happens when neither atom wants to just give away an electron? What happens when they're a little more evenly matched? Well, then they have to learn to play nice and share. And this brings us to the second major type of bond, the covalent bond.
So instead of a transfer, a covalent bond is all about partnership. It's a team effort. 2 atoms come together and agree to share some of their outer electrons so that both of them feel like they have a full, stable shell. So this time, the key word isn't transfer, it's sharing.
Let's actually build a water molecule to see how this works.
You have oxygen, which needs 2 more electrons to fill its shell. Then along come 2 little hydrogen atoms, and each one has 1 electron to offer. So the oxygen atom shares one of its electrons with the first hydrogen and another electron with the second hydrogen. And by doing this, everyone's happy. The oxygen feels like it has 8 electrons, and each hydrogen feels like it has 2, which fills its own outer shell. It's this beautiful sharing system that creates the stable water molecule that is, absolutely essential for all life.
Okay, so we've seen how atoms can give, take, and share electrons to make these bonds. But what does all this tiny atomic-level stuff mean for us in the big picture? Well, it means everything. These tiny interactions are literally building the world around us every single moment. I mean, just look at how fundamental these changes are. Respiration. That is the chemical reaction happening in your cells right now that's giving you the energy to watch this. Photosynthesis? That's the reaction plants use to create the food we eat and the oxygen we breathe. And combustion? Like a campfire or your car's engine? That's a rapid chemical change releasing massive amounts of energy. These aren't just things in a textbook. They are the engines of life itself. So when you really boil it all down, everything comes back to these simple rules. Atoms are always searching for stability. They form bonds by either trading or sharing electrons. And in doing so, they create every single substance we know, and they power every process that we rely on. It's just an incredibly beautiful and elegant system.
So, now that you're in on the secret, now that you know the difference between a physical and a chemical change, and you know about the bonds that drive everything, I've got a challenge for you. As you go about your day, what chemical change are you going to notice next? Maybe it's cooking dinner, striking a match, or just watching the leaves change color in the fall. The chemistry is always there, just waiting for you to see it.